Hey everybody, welcome to the Weekly Space Hangout. My name is Fraser Cain. I'm the publisher of Universe Today, and we have all of our friends this week gathered together to talk about mostly about inflation and confirmation of inflation in primordial gravitational waves. So, and I am so glad we've got an all-star cast. Now, yes, I'm in a new location. Get over it. Moving on. So we've got Brian Coberline. Hey, Brian.
Hi.
From RIT. Dr. Matthew Francis. Oh, I could not be happier. We've got Dr. Matthew Francis versus Brian Coberline. Oh, this is the best. Mike Simmons from Astronomers Without Borders. Hey, Mike.
Hi, Fraser.
We've got Morgan Renberg. Hey, Morgan.
Hi, Fraser.
And Dr. Nicole Gallucci.
My audio works now. Yay!
Yay! That was close. It almost didn't work. What did you do? You turned it off, turned it back on again?
Yeah, I reset the PRAM. Mike can tell you, on Wednesday night, my speakers just decided to flip out and make this really high-pitched... Well, you didn't hear the noise. They made this really high-pitched noise just as I hit broadcast. So I had to let the computer run the Hangout without me while I went next door to George's office.
It was a learning experience.
It was a learning experience for learning space. That's
for learning space. Exactly. Let's learn how to use our computers. Let's learn that we can't trust computers, that we're one step away from the total robot apocalypse.
I'll be the first against the wall.
Yeah. I, for one, welcome our screeching computer overlords. All right, so this week we've literally got one topic.
No, we don't.
One big topic that's going to just consume us all, and every time
because somebody canceled last week when another organization had a big press release.
And Matthew get tired, I will rile them up and send them back into battle against each other. It's just going to be a knockdown, drag out fight. So I'm really looking forward to this. But in addition, perhaps, maybe. We might also talk about some other things, such as how people can map the moon, just like the pros.
You're such a good partner, Fraser.
We'll be talking.
Such a good partner organization.
We'll be talking about waves on Titan, and I would love for us to talk a bit about Cosmos because that's apparently what everyone does all the time. Is talk about Cosmos. Some people even do live shows right after each episode where they talk about it, which is our good friends over at Astronomy Magazine have been doing that, and Discover have been doing a wrap-up. And also there's a bunch of exciting stuff happening in the sky shortly, and normally that's Dave Dickinson, but Mike Simmons knows as much about all that stuff as anybody, so he'll be catching us up on that. So without further ado, let's talk about the show Cosmos. So who watched it?
I did.
Yeah? All right. Did we like it better than the first episode?
It's hard to tell. I'm live tweeting while doing it, so I'm not terribly paying attention.
You're live tweeting Cosmos, not actually watching it and really taking
it. Well, I'm watching it, but then I'm saying that, and it's a community experience, really.
I thought it was better. Cosmos is maybe the biggest public stage that science has had in a decade or 2 decades, maybe even since the last Cosmos. And in episode 2, they came right out and answered the biggest question that is out there about science today. Is evolution real? Is it fact? Is it supported by science? And they came out and teed up on every one of those and gave a very strong, unflinching answer to each piece of that, and backed it up, I thought, with really clear, really lucid explanations of various concepts related to evolution and natural selection.
And they had this great graphic where they had the creature, they showed the evolution of the eye. So they really
that was amazing.
That's the toughest, or the thing that the creationists go after as much as they can, and they picked this as their example, and then they showed you like the first version of what a light-sensitive cell might have looked at and what perception of the creature, and then they evolved it step by step and just showed you what each one of these different eyes might have given the creature, and how each one was a very useful evolutionary step. And the great part was when they got to when the creatures crawled up on land, they still had these ocean-based eyeball, which was not that useful for in the air, and so how evolution adapted. So I thought it was terrific. I really did. I thought they're really hitting their stride. Anyone else? All right, let's talk about inflation. I can't put this off any longer. All right, so what's the big news? Brian, can you give us the big intro?
Oh, you're letting him start.
Well, here's the basic overview. There was a team that was called Bicep 2, and they looked at light from the cosmic microwave background. So they're looking at this background microwave glow, and specifically they're looking at an aspect of light known as polarization. And basically, because of the variations in temperature in the cosmic microwave background, the light is polarized. And the standard way in which it's polarized is known as E-mode polarization. And as that light travels to us, a lot of things can happen to it. One of the things that can happen to it is that it can be gravitationally lensed. And that gravitational lensing can kind of twist that E-mode polarization into something called B-mode polarization. So they were looking at B-mode polarization. The other way in which you can get B-mode polarization is from strong gravity waves from an inflationary period. So if you have these gravitational ripples caused by the inflationary period, that would also cause B-mode polarization. So the key is distinguishing this kind of primordial cosmological B-mode from gravitational lensing B-mode. And they were looking at that, and the claim that they make is that they have found this primordial gravitational waves, B-mode, that is a strong signal as evidence of cosmological inflation.
I didn't understand a word of that. Matthew Francis, could you extend upon that?
Okay, let me start back with inflation for a moment. Basically,
No, I totally got it. I totally
okay, well, I know that. I'm just saying I'm going to fill in some of the gaps in Brian's explanation. Maybe we can kind of make we can complement each other.
All right, is my sound still a little weird? I plugged in my microphone better. That help?
It sounds like Daft Punk.
Is it still sounding like Daft Punk?
Yeah, it's just you though.
Yeah.
It is just me. Well, then I am going to abandon this microphone.
I was hoping you'd sing better, faster, stronger, more.
Yeah, I apologize. Hey,
Anyway,
I've abandoned this microphone. This microphone is no good to me now. Do I still sound like Daft Punk?
No, you sound better.
Okay, all right. Please continue, Dr. Matthew Francis, to fill in some of the gaps.
okay, so basically, the universe on the biggest scales, which is much bigger than galaxy clusters, much bigger than any single structure we see, is remarkably smooth and uniform. Incredibly so, far too much, because if you look at 2 points on opposite sides of the sky, those 2 points basically have never been in contact with each other since the beginning of time. That's a pretty impressive thing. So why should they look like each other? Why should they be the same temperature? And so that's one of several problems in the vanilla Big Bang cosmology that we have. And so in the late 1970s, early 1980s, a group of cosmologists tried really hard to figure out how to fix that problem. And the solution that a lot of people settled on was something called inflation. The idea is that during its first instance, the universe, it was a trillionth of a second after the Big Bang, the universe expanded very, 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 very rapidly. I think that's far too few varies.
Like
acceleration
of light rapidly, right?
Well,
yeah, it's okay.
If you were to take the inflationary period, 2 people standing next to each other in the next instant would be a light year apart.
Right.
That's the scale of which it's a factor of 10 to the 26th.
Yeah.
So that's how big inflation is.
It's not even it's barely even comprehensible, even if you're used to dealing with big numbers.
That sounds like 7 varies, I think would be appropriate.
Nah, I think more like 10 to the 22nd.
10 to the 26th varies, okay. Yeah.
So, but the thing is that this is, in some ways, inflation is kind of the worst idea except for all the others, because nobody has quite figured out exactly how inflation should work, despite having over 30 years to work on it. And so most of us are pretty sure that inflation happened. Something like inflation must have happened. But we don't have a lot of direct evidence for it. And so that's why this particular result from the BICEP 2 experiment is potentially very important, because, as Brian was saying, inflation could have produced all of these primordial gravitational waves, these ripples in space-time as it happened. But here's the deal. Inflation is not the only thing that could have produced primordial gravitational waves. And also, as Brian pointed out, there's other things that can produce B-mode polarization other than primordial gravitational waves. So this BICEP 2 result is really, really cool. But do not pop the champagne yet about Nobel Prizes. Do not pop the champagne yet about the discovery of primordial gravitational waves. And believe me, no waves more than I do. Right. Nobody wants them more than I do, because this would be the most awesome thing. You know, I will be the first to be jumping up and down and screaming if this result is borne out. But we still have some work to do, and the next 8 months between now and the next data that's released from the next set of experiments that are doing similar measurements, theorists are going to be working really hard to understand the BICEP 2 results. Other people are going to be analyzing the data, and this is great. All the data is public, so everybody can download this. Everybody who has the expertise can look at this, and they will be. We're going to see a lot of papers, probably too many, but we will know in the next 8 months. We will have some really good ideas about what's going on. Another thing that's important to point out is that there's a significant discrepancy between the BICEP 2 results and earlier estimates on how big this B-mode polarization should be. And admittedly, those other estimates are based on indirect measurements. So it's possible that we can get around that problem. And honestly, again, we're kind of hoping in a way that this result is correct, because that means not only were there primordial gravitational waves, there were a huge amount of them, a lot more than we expect from other measurements.
Okay, so I've got about 8 questions here that I'll need to sort of line up here. So Brian, can you first explain what is a primordial gravitational wave?
Well, a gravitational wave is a distortion in space-time. We've seen indirect evidence of gravitational waves before, for example, in a binary pulsar. In this case, the primordial black waves, the
can't say black hole, because
I keep wanting to say that.
I know you want to say primordial black holes.
I don't mean to. When you have this inflationary period, at least this is the inflationary way to go over, and that's the one I'm familiar with. I know there are other ways you can produce these primordial primordial gravitational waves. The thingies that wave. The idea with inflation is that when you have this rapid inflation, it's causing these distortions within space and time, and it's almost like ringing a bell. It's like bang, and then the whole thing just rings with these gravitational waves. And these ripples were formed in the earliest moments of the universe, and so that's why they're primordial gravitational waves.
Now, if I understand look at gravitational wave in sort of the traditional sense, when you have massive objects that are moving around in space, you get this distortion of space-time, and these ripples move out, as you said, like ringing a bell, and they actually are sweeping, theoretically, although they haven't been detected, as they sweep past us here on Earth. Our length or width or height actually change like a wave as this gravitational wave passes through us. So I might be, X number of centimeters wide, and then as a gravitational wave passes through me, I will get a micro fraction wider, and then it'll go back as this gravitational wave passes through me. So are these primordial gravitational waves, are they the same thing? Are they kind of rippling around and bouncing around, maybe not bouncing, but rippling through space right now, and is this what's been detected? Right.
They are, and in a way, I mean, they are the same type of waves, but on a large scale, they have a very specific pattern. So the locally produced ones are very clear. They're coming from a source and radiating outwards, and these are on a cosmic scale.
Okay. So then, and Matthew, when you talk about the BICEP experiment, so what is this experiment? What actually did the scientists do to make this calculation?
Well, basically, when the universe became transparent, about 380,000 years after the Big Bang, a whole bunch of light just was released all at once, and that's what we call the cosmic microwave background. I think my beach ball's out of reach. Somebody else probably has one in their office, though. What the fact that there are these waves left over, or possibly there are these waves left over from the inflationary period, means that the light is passing through the ripples and getting distorted as it goes. And you can tell by the way I'm moving my hands how it gets distorted. But it gets twisted around because you've got all these frankly random ripples. They're not coherent waves like you get from a binary pulsar. They're very messy, and so that's exactly what we see. Oh, there we go. We've got the W map on Morgan's screen.
Yeah, here.
And these are temperature fluctuations we're seeing here. Polarization is more subtle than that, and it's a lot harder to detect. That's part of the reason why this BICEP 2 result is a really big deal, even if it turns out we have to modify it, because this is a very hard problem to solve. Yeah. We have to hand them all sorts of praise and kudos for this, whether or not we refine what we think.
Yeah, now, when I think about polarization, like the experiment I like to do with my kids with polarization is when we're in the movie watching our 3D movie and we've got our 3D glasses, and I always have them take their various 3D glasses and push them together in different ways, and you can actually see how the 3D movies are using the polarization of light. That that light is coming at us, and it's coming in horizontal, it's coming in vertical, and normally we see with our eyes, we're seeing it all jumbled together. And the trick with the movies is that they're shooting some light polarized one way, some light polarized the other way, and then when you wear the lenses, the one lens blocks the horizontal, and the other lens blocks the vertical, and so you get two different images coming into your eyes. So is it anything like that?
That's what it is. I mean, the polarization, because of the light waves, they're called transverse waves, but because they have an oscillation that's perpendicular to the direction of motion, that oscillation can have an orientation. And if it has that orientation, that's polarization.
But how do you see the gravitational waves as expressed in the polarization of light? That's the part that's...
Well, if you look at an image of like a gravitationally lensed galaxy, okay, you can see that the galaxy that's being lensed is distorted. It's kind of warped and twisted a bit, okay? Well, if you have, say, a light wave that's polarized this way, when it's gravitationally lensed, it can be warped and distorted too. So it can be twisted into different orientations. And so that E mode can be twisted into a B mode form. These gravitational waves are doing the same type of thing. With the gravitational lensing, you have a localized mass that has distorted space and time around it, and that's why you get a gravitational lensing. In this case, the gravitational waves themselves are distorting space and time, and you're getting a similar type of distortion.
So, and Dr. Matthew Francis, so if this is correct, and it is a sort of, I guess it is a confirmation of this concept of inflation, this way to explain, literally this way to explain, why don't we see the left side of the universe and the right side of the universe connected together, that they just move too quickly, too early on for us to be able to see, to see reflections in the universe. What does the sort of the sensitivity of the experiment they've done so far, what does that tell us about how correct inflation is, or how precise inflation is, or the rate of the expansion, or anything? Does this help us sort of put some guidelines in and some constraints on inflation?
Well, that's a really good question, because we don't know enough yet. It is one thing to confirm inflation, and it's another thing to say this is going to, what this tells us about a specific version of inflation. Inflation is less a theory than it is what you have before you get a real theory at this moment. There's a lot of versions out there. And so the nice thing, though, is that it might actually have a kind of a filtering effect on our theories. Just like WMAP and the Planck measurements of the cosmic microwave background, we're able to rule out certain models of inflation. As we study this data more, we should be able to rule out even more. So whether one will be left standing, the simplest form, I believe, still stands based on what I've read. I haven't gone too deeply into it because, frankly, I think it's too soon. I think we're going to, I'm kind of taking the attitude, let's let other people, the experts in this area, slug it out, and then when they're done, I'll write about who's left standing. But that's my method. But I think we may see a theory stand. I'm actually kind of interested in another possibility, which is that this result may not correspond to anything we know right now, any inflationary model, and I think that's actually a distinct possibility. If I'm right, I almost feel like making a Stephen Hawking bet on that one, because I think it's distinctly find that, yes, inflation is borne out, but not any version that we currently have. That's probably because I'm perverse, but it's also, I think, based on the fact that we don't have a good single theory of inflation that stands head and shoulders above the others. They all have some problem with them.
Right. So it may be not one of the popular ones, because honestly, I don't know how many exact inflationary models there are.
Too many, but a lot of them are pretty elaborate too.
Yeah.
Now, if this does get confirmed, do you think it's Nobel Prizes all around?
I don't know who gets it.
Yeah.
The one who, I mean, is it the original inflation theory, or is it the one who got the right model, right?
Well, I mean, that's a good question. Alan Guth's original version is very nice, and it's wrong.
Yeah.
Right.
I mean, it's a lovely theory. It just doesn't happen to correspond to reality.
Yeah, it's a great idea that doesn't work.
Now, Brian, you've been trying to say primordial black holes. Isn't one of the sort of implications of inflation and these ripples of these gravitational ripples is one of these ideas? These gravitational primordial black holes. I want to say primordial gravity waves. I don't know what it is about.
It might be. I mean, I keep saying primordial black holes because that was my dissertation. So it dealt with primordial black holes. Like, you went primordial black? No. I actually don't know. I don't know if it would alter the idea. I mean, primordial black holes are a part of early cosmology models anyway. So the inflationary period, how that would affect the primordial black holes, I'm not sure. I just haven't looked at it in a long time.
Okay. Does anyone want to ask any more questions or add anything about this? Anyone, the viewers, do you feel like you understand this enough to be able to, at a cocktail party, for example, entertain your friends and colleagues? So, and let's see, there's a couple of questions here. This comes from Shivang Gupta. What could the other sources of B-mode polarization be from that time, just after the Big Bang? So, either Matthew Francis, do you know of what any other sources of B-mode polarization might be?
Well, the one, and Brian mentioned this already, the one that can kind of mimic. B-mode polarization comes from two possible sources. It comes from gravitational waves, but it can also come from lensing. And lensing is stuff that's in between us and the cosmic microwave background, so to speak. It's the photons we're seeing come to us 13.8 billion years without hitting anything in between, but they might have passed through some stronger gravitational field which will twist and turn them around. And so one thing that we have who are talking about this is, I think it was what all the professional cosmologists I was in contact with on Monday were talking about during the press conference and the discussion of the paper, was whether or not the model that they fit the BICEP 2 data really fit the model of gravitational waves plus gravitational lensing. Right. Whether there's other possibilities, I think not. I'm don't think there's anything else that can mimic those two things. So it's really the question of whether it's, one, whether we're really seeing B-mode polarization, and two, whether it's coming from lensing and gravitational waves, or the balance is off.
Right.
Okay.
One of the things to keep in mind is you have E mode and B mode, and you have two different types that you can have with B mode. E mode polarization is easier to find than any of the B modes, and B mode due to lensing is easier to find than B mode due to gravitational waves. So what they've found here is they have clearly found B mode polarization. I don't think anyone's disputing the fact that they have found B mode polarization on a cosmic scale.
Yeah, well, I should correct my statement. Yeah.
Yeah. So the question that a lot of it is being debated about is, do they have a strong enough signal of primordial gravitational wave B mode, or is this predominantly just lensing B mode? That's the real question. And that's still being debated, because depending on how you look at it, the original paper that they are submitting for publication says that it's at 5 sigma, which would be an absolute valid thing. You can look at the data in other ways and say, well, it's more like 2.3 or 2.7 sigma. That's not a confirmation. So one of the things that's going to be in peer review is, can they make the 5 sigma claim, or is it really not that strong?
As we all call Higgs boson, we want 6 sigma.
We want 6 sigma. Well, 5 sigma is usually considered the cutoff. So, and I think they 5.8 or 5.9.
Okay, so Tatiana Velishevka, sorry about that.
Mike knows how to pronounce it.
Valevska.
Oh my gosh. No, Tatiana Vasilevska.
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 I cannot imagine gravitational wave. What does it look like? Funhouse mirror.
Yeah.
So imagine walking past a bunch of funhouse mirrors, but instead of it just being the image of what you are, it actually being you stretching and shrinking. So, fun. Good times. But painless. Rich Hayward asks, does this inflation discovery have any implications for alternate theories like M theory? As we all learned in True Detective, with M theory and brain theory, the universe is like a wheel, and it all just comes back to the beginning or something. So, any implications? Inflation, M theory, many universes colliding, strings.
Do you want to go, Francis? Do you want me to?
I'm gonna let Matthew Francis take this one.
Oh, that's a good question. So this is a tricky. Again, this is something I'm not particularly an expert in. So, and again, like inflation, there's many different versions of what's called brain worlds. Not BRANE, not BRIN. But it's the idea that our basic. It's even hard to visualize, but basically our universe is one of several that exist together, and they interact with each other because gravity can leak across the extra dimension that separates them. And there are several models that involve collisions between these, and that's what this brain collision idea is. I feel like my brain's colliding sometimes. But some of them, I'd say the simplest versions do not produce gravitational waves in their inflation. They don't have inflation like the Big Bang plus inflation model that we've been talking about does. They have this tension between the brains, has the same effect, but it's a different cause. But at least some versions don't produce gravitational waves. But I've heard people say that other versions do, and that's where I have to throw up my hands and say I don't know.
So Nancy Graziano asks, what do you feel is going to be the next big discovery, breakthrough, confirmation? So Brian, specifically in this field. So, I mean, imagine we launch the the Cosmic Polarization Explorer mission, and its only job is like the WMAP, but all it's doing is searching for measuring polarization of light, we could get this to a very precise thing. So what do you think is going to be the next big discovery that we're going to be making on this?
Well, I mean,
or are we now just cleaning this up? And by we,
no,
I
no.
mean
There is Planck, and Planck can measure polarization. So there is polarization data that's going to come in from Planck that's going to be compared to this. I think if you look at the next level is going to look at the connection between the gravitational waves and the density fluctuations, because there's a way to compare that to actually distinguish between different inflationary models. And that would be the next step, is actually getting high-resolution observations of the gravitational waves. If, in fact, that's what they're for, then we would start paring down which inflationary models fit and which inflationary models don't. We can do that to some degree with the data that we're going to be getting. But I think the next big breakthrough would be, aha, this theory, so-and-so's theory, is the inflationary model, and that is the one that the universe did. That would be the next breakthrough.
Okay. I think we're good. Oh, one question from Adam Synergy. Does the BISEP 2 result indicate that gravity is quantized? I think we've lost. Oh, Matthew Francis is put up.
Not that I know of.
No. Okay.
I don't know of anything.
We're not at that level yet.
Yeah.
The idea is that if there are primordial gravitational waves, then they must be produced by some kind of quantum process.
Right.
Okay. Well, let's. So that's good. So we'll. I'm sure we're going to be watching this. We're going to be doing follow-on episodes of the Weekly Space Hangout where we give you guys all an update, and hopefully this gives you enough of a background so that when we talk about it in shorthand and go straight to various modes of polarization and such, you'll be ready to go. So why don't we move on? I'm going to move on to Dr. Nicole Gallucci, and we're going to talk about finding craters.
First, I want to know what is Matthew showing?
He's showing
This is using Charlie Brown's head as a gravitational wave detector.
Okay, just check. That's what I thought, but I was just checking.
I gave a talk years ago called Charlie Brown's Guide to Gravity,
Wow.
and I realized that Charlie Brown is like the perfect person to use as an example for all of this stuff. So I used his head as a detector.
Awesome.
But I think we don't have time to explain it. So maybe I'll write a blog post and dodge the syndicate lawyers.
Yeah, good luck with that.
So, but anyway, I surrender the.
Okay, so we had a very interesting story. This was actually a big moment for CosmoQuest in that last week we put out a press release saying that we had this huge paper that the PI Stuart Robbins has been working on for months and months and months, accepted in the peer-reviewed journal Icarus of planetary Icarus is about planetary science, basically demonstrating to the world that all the work you've done with moon mappers is totally valid and totally awesome and just as good as the experts. So I can screen share one of the main images from this. Oh, someone's already got it. Ha! Someone beat me to it. Sweet. Okay, so at the top are different expert identifications of craters. These were done by 8 different crater experts that range in experience from a few years to a few decades, using pretty much their own tools that they like to use. And those results show that there were differences up to as big as a factor of 2 just between crater experts. And so it really hasn't been studied in much detail how different experts rate different craters or measure different craters. As you can see, they're all off a little bit from each other. So even though this is a quantitative process of measuring and counting, everyone's going to do it a little differently. And so that has effects back through the whole history of the literature of crater counting. And then we compared the moon mappers classifications. You can see that on the bottom, and those are the red circles, all the individual classifications. And although there's a lot more variance between the volunteers, when you average together the volunteer data, once you've gotten at least about 7 or 8 people, different independent people that have looked at and marked the craters, it is right on par with what happens when you average the experts together. So you actually are eliminating personal biases from having one crater expert map it. but when you recruit a whole bunch of citizen scientists to map it, you're getting rid of some personal bias, and you're getting it done a lot more quickly. So this was one particular image that was done by the citizen scientists and by the experts, but in order to map all of the imagery that's coming back from LRO, which is our goal, we need a lot more work to be done, and for that we need all the volunteers we can get. And so this big news, big paper, we've got a press release up on CosmoQuest. For some reason the paper is caught in the queue in the archive, so the free version of the paper is not quite available yet. It's behind a paywall at Icarus, but we've submitted it to archive and we're waiting for that to unstick from the queue. So you all can read it. It's a huge paper. I'm probably going to be blogging about it with Stuart and I are probably going to try and get some of this stuff teased out from the paper and blogged about on the CosmoQuest site. So you can, if you're really interested in the nitty-gritty details, you can take a look at that. We'll be working on that. So that is our demonstration of the results that you guys have done, you guys have worked on, all you crater mappers out there, and an invitation to anyone who hasn't tried the project to come check it out. We have a lot more Moon, Vesta, and Mercury that need to be mapped.
So this is confirmation of the theory.
Of the method of citizen science,
of citizen science, that regular people who just love science and have some time to spare can contribute in a meaningful way and get some work done that pushes science forward, and this is great. And I think a big kudos to you and to Pamela and to the rest of the CosmoQuest team for just making this thing happen, and all of the outreach and effort that's been going on over the years, culminating in a serious, significant paper showing that this is legit. And I know that those poor scientists who had to just go and classify those craters are so grateful that this army of volunteers is out there. And I think, this is really part of what we're trying to do with CosmoQuest is, like, we know that you love space and astronomy, and even though you're working as a doctor or a engineer or, you're going to school for something else, you really want to be in space and astronomy. And instead of dropping everything and going back and doing what Nicole and Brian and Matthew did, you can just jump in at whatever level you have and contribute to meaningful science research. And in fact, with the other courses, which I don't know, have your courses filled up yet, Nicole and Matthew?
We still have one by Peter Dove, the astronomical imaging course. That starts in about a week, Matthew?
Yeah. Starts on Tuesday.
It starts on
time.
Oh.
Right. In addition to your raw human ability to distinguish shapes, we want to teach you more. We want to teach you how to recognize alien life. We want to help you learn planetary geology and cosmology. So
I want to get you guys doing radio astronomy. I'm still working on that one.
Yeah, looking for the next wow signal. So so I think this is great. And so if you're interested in science, if you have this in space and astronomy, and you have this sort of sadness that you didn't become the astrophysicist that you always knew you could be, we have all of the resources available to you to take that to the next level. So such great work, Nicole. Awesome.
Yeah, so I'm very excited, and like I said, we did a set of video tutorials which you can watch that'll kind of get you started, tell you how to do it, or we've got screenshots that show you how to do it too. So you can kind of pick whichever way you want to learn. It only takes a few minutes to get set up.
Not to steal anyone from moon mappers, but if for some crazy reason planets aren't your thing, I think Sloan Digital Sky Survey, you can do a similar thing with galaxies and finding and classifying galaxies for them. So if that's more your thing, there's a lot of ways to get involved.
Yeah, absolutely. That's the bigger theme, I think, is just really recognizing that regular folk who have a lot to contribute, and there's a way to bring this together. I mean, the birders have been doing this for 100 years, and other scientists are starting to have the tools that they can do this as well. Okay, so now I'm a sailor, Morgan, and I'm not a big fan of waves, though, and so I was all set on taking my boat to Titan. What am I looking at?
Yeah, well, so first off, you'd still be pretty safe to take your boat to Titan unless you made your boat out of, like, paper mache.
Might have.
So Titan is one of the most remarkable bodies in the solar system. It's the only moon in the solar system with a meaningful atmosphere. In fact, its atmosphere is thicker than that of the Earth's. And it's also the only other body in the solar system, planet, dwarf planet, moon, to have liquids on the surface other than the Earth. Unfortunately, the former fact that there's this big, thick atmosphere makes it rather difficult to observe the latter. And so I can try my hand at sharing another picture here. So this is a map of one of
the black screen.
Getting
you
the
shared
black
too many times. Oh no, there it is. Now it's coming.
All right. So this is one of the poles of Titan as seen by the Cassini spacecraft in orbit about Saturn. And what you can see here, these white areas are places they don't have data. These big black areas are regions that are extremely flat on the surface, and this is measured by bouncing radar off the surface and watching it come back. And these really flat areas, cleverly colored blue, have been interpreted as lakes of liquid methane. So it's about 180 degrees below 0 centigrade on Titan. So there's no liquid water here. Water's as hard as rock. But we do have liquid methane, and it's formed all of these presumed to be lakes that we see. But every time we made a measurement of how flat these lakes were, we found them to be basically as flat as you could possibly measure within the tolerances of the observation. And so people use that to conclude that there wasn't any waves on the surface. But that's changed just this week with a talk from the Lunar and Planetary Science Conference that found possible evidence. I want to strengthen that possible evidence for waves on the surface of Titan. And this evidence comes from 4 pixels in various observations of the surface that were a lot brighter than they expected. And of course, this can happen, like with any other measurement, just due to random error. But they're pretty sure that these are actual real fluctuations. But they don't have to be waves. They could be an iceberg, has been another suggestion. Another reason maybe not to take your boat there. But it could be an iceberg. It could just be like a shiny mud flat also. So we're not sure that it's waves. But if it is waves, they're really small. And we're talking just centimeters high. So these are like ripples in a pond more than thinking ocean waves. But that could change in the coming years. Saturn takes quite a while to orbit the sun, and the system takes quite a while sort of to rotate on its tilt, just like the Earth rotates, or just changes which angle it's pointing towards the sun. And so that means the seasons are very long. And we're just starting to enter spring at Saturn. And of course, we know here on Earth, when you get spring, it warms up. And when you have these warm, rising currents of air, you can start to generate wind. And wind is the primary driver of waves here on the Earth. So if we come back in a year or 2 years, and fortunately Cassini will be around hopefully for at least the next 2 years, we might start to see these centimeter-sized waves really picking up into what you might actually consider waves and not just ripples bouncing around.
Awesome. I think that, another good reason for us to send a sailboat mission to Titan.
Yeah, well, so when Cassini landed the Huygens probe on the surface back in 2005, and it took images of the surface, they actually did design it as a boat because they were very hopeful that it would land in a lake. In fact, they hadn't even confirmed that lakes were there yet, but they expected them, and they designed the probe to float around in the lake like a boat if it happened to land there, but it ended up landing in like a desert instead.
That would have been really cool if it had landed on a lake. That would have been like a discovery of liquid on Titan and images from the surface of Titan all at the same time. That would have been amazing.
No kidding.
Yeah. Okay, great. So we've got a little more time left, and normally this is Dave Dickinson's job, but I know he's busy today. We've got Mike Simmons, who is from Astronomers Without Borders, and there's a few events that are coming up in the next couple of days, weeks, months that people might want to be aware of. So Mike, what do you want to talk about?
Well, I'm going to talk about just April because I think there's enough going on then for people to know about. And some of it's available online, so even if you can't get to it, or if you had success like the recent asteroid occultation of the bright star Regulus, which I'll mention real briefly. which was completely clouded out everywhere. There are a lot of things that you can see that are going to be pretty cool just over the next month. So I'll mention first, because I know a lot of people have heard about this unusual event where an asteroid, which from Earth is a really, really, really tiny object, went straight across in front of the bright star Regulus, one of the brighter stars in the sky. And this was big news, and there were people all over in this long path. You had to be in just the right spot in order to catch this, that were observing it. And there hasn't been a single report that I've seen of anybody seeing that successfully. It's been cloudy every place, mostly along the eastern coast of the United States. And just so people understand why this is more than just cool, that's scientifically useful, is by seeing exactly where people can see it, where the star blinks out, and where it doesn't blink out, even though we can't see the asteroid itself and get its shape and size. You can figure out from basically the shape of its shadow, where that shadow sweeps across the ground, where people see it and don't see it, what the shape of the thing is. But you need a lot of observations, and I'm afraid that didn't happen this time. So that's a scientific reason for it. And even though, well, you know, we've gone to a few asteroids, but there are millions and millions of them out there that we haven't yet. So it's very useful.
Well, and it could have been like one of the possibilities was that we might have been able to discover a moon for the asteroid. And again, so no observations, no data. No moon. No moon. Yeah, and that's a possibility. It's really tough because things have to be just right, because that moon could be anywhere around the asteroid, and it's going to be a really fast blink of the star. So that's the kind of thing you'd want to have several observations of. It's pretty tough, but it is possible. But you know, when it's cloudy, everybody's got an equal shot, which is 0. So. But I think it would have been neat if you had lived in that corridor and it had been clear. Regulus is a really bright star, and so you would have literally, if you there, you would have watched Regulus sort of fade away, while all the other stars were just stayed the same. So it would have been pretty neat to see it. It's really unfortunate that everyone was clouded out.
Well, that's the thing. That stars are really just points of light, actual points, and they don't have any size.
Yeah. And Regulus is a big star, big bright star, and from the distance of Earth, it's so small. Like Morgan says, it's just a point of light, and you just see it blink out. And if you didn't know what was going on, it would be really freaky. But it would come back. So there you go. Now, also in terms of things disappearing in the sky. There is, I want to mention that there's a total solar eclipse. Lunar eclipse. April 29th. Well, no, there's a total solar one, yeah. Yeah, this is 2 weeks after the lunar eclipse. That's not just a coincidence, but I think everyone can figure that one out. They happen at new moon. Lunar eclipses happen at full moon. And that's on the 29th, but that one is primarily for penguins because it's a narrow path in Antarctica. It does go up the coast of Western Australia, and hopefully there will be people there. I'm sorry, this is not a total solar eclipse. It's an annular eclipse. So I made my notes in error here and just read them without thinking. But an annular eclipse is when the moon is not quite big enough to block out the whole sun. So you get a bright ring of the sun's chromosphere, the bright part of the sun around the edges. And there are a lot of interesting phenomena associated with that as well. So we hope that all those millions of penguins get a good view, and also some people in, I'm sorry, I said Western. Apparently when I go to the Southern Hemisphere, I get everything backwards. It's Eastern Australia, and so there could be some people viewing that, but it is a partial eclipse for all of Australia and a lot of the South Pacific. Now the bigger event, and this is visible to people all over, technically, a solar eclipse is really an occultation. It's one object, the moon, getting in front of the other object, the sun, and blocking it out. A lunar eclipse is when the moon actually goes into the shadow of the Earth. So it's blocked from the sun by the Earth. So it's technically it's not. It's well, this is an eclipse. The solar eclipses are occultations. But we won't worry about that. It all looks the same. And what's cool about the lunar eclipse, now this will be visible, and let me see if I can bring that up here. I think I might get a black screen for that, but you tell me. Oh, here we go. Yeah, I think that's working. Got it? Got it. Okay, yep. So what we have here is a diagram that shows how the moon is slipping into the Earth's shadow. That would be marked as the umbra there, which means, strangely enough, shadow. And the penumbra is where it is partially covered. The sun, part of the sun is shining on the moon. So it'll dim, and it goes completely dark, the darkest part when it's in the center there. Now you see it's shown as kind of orange. And this is what it looks like, because the shadow has a rim, it has a red light that's streaming through the Earth's atmosphere and bending. It's sort of like getting a sunset on the moon. The light refracts in the edges of the atmosphere around the Earth. So if you were on the moon looking up, you would see the Earth's night side, but around the edge you'd see some light from the sun coming through, and that would be reddish colored. So the moon can look very red. And weirdly, this is a rare phenomenon where the weather on Earth affects what you see in the sky. So if it's cloudy everywhere around the edge of the Earth, then it gets really, really dark, and if it's clear, it's a bright red. So you never know what you're going to get with this. And that is visible. Down here, you can see at the bottom part of it, you can see a map of the world that shows that the entire eclipse is visible for most of North America and the western edge of South America. It's going to be partially visible from other areas. You aren't going to see anything from much of Asia and Europe and the eastern half of Africa. But hopefully there will be people that are broadcasting this, webcasting it, such as David, who I'm trying to fill in here for, which is a difficult task, and some other people. And this is on a, let's see, I think it's during the week, but it would be a cool thing for virtual star party or something.
Yeah, we're definitely going to be broadcasting it. I know Scott is getting organized, and we've got a couple of astronomers that have committed to broadcasting it, and we'll definitely be showing off the eclipse when it happens. But for me, it's great. It's literally, I'm at the center of it. On the west coast of North America, it's just going to be absolutely perfect. So I want to try and watch with my own eyeballs. So we're running out of time now. So just remember, make sure you set some time aside, either to watch it in person or through the internet if you have to.
Absolutely.
That's great. Thanks, Mike. Okay, so we're going to wrap this up. I'm going to give people a chance to shamelessly self-promote themselves. Brian Coberline, where do we find out more?
You can find me at briancoberline.com or on Twitter at briancoberline or on Google+, where I post every day.
Awesome. Dr. Matthew Francis, where do we find out more?
You can find my professional site at bowlerhatscience.org, also on Twitter at Dr. M.R. Francis, blog at Galileo's Pendulum, and also put in one more plug for our upcoming online classes at cosmoacademy.org, including one that starts next Tuesday.
All right, Mike Simmons, where do we find out more?
Well, the main thing is here, and I'm going to share this because people have seen me already, and that's no need for that. Astronomers Without Borders, April's Global Astronomy Month. You can watch some events there that I didn't have time to talk about online. Some observing events, more about the Mars opposition, and seeing that online, as well as some asteroids and other cool things. So go here. It's Global Astronomy Month. It's gam-awb.org or astronomerswithoutborders.org, and learn what's going on and how you can participate and learn more than I had time to tell you about.
All right, Morgan, where do we find out more?
Yeah, well, first off, if you had a question today that you didn't get answered, I'll be answering those this afternoon on the Google Plus Space community. So if you head over to Google Plus, you choose Communities. Space, I think, is about the biggest one, and I'll be there answering questions about all these topics and anything else you might have for the rest of the afternoon here in the United States. You can find me at cosmicchatter.org or on Twitter at cosmic_chatter.
That's fantastic work. Yeah, you've been doing this several weeks after the Weekly Space Hangouts, and I think that's just absolutely terrific that you go into the space community and take on all comers, people's questions about space and astronomy. I think that's just fantastic. So if you want more follow Morgan to the space community and just hit him with questions. The harder, the better. Nicole Gallucci. Dr. Nicole Gallucci, where do we find out more?
I live on the internet as Noisy Astronomer. You can find me under that name. And I work over at CosmoQuest, so come to cosmoquest.org and do science with us. I'll probably be tweeting along with Cosmos again and working on the Mappers projects during the commercial break. So let's see how many images we can get done on the commercial breaks for Cosmos.
That's awesome. I'm sure Fox really appreciates that.
I'm sure they do.
Okay, so of course I am the publisher of Universe Today. You can always check out my YouTube channel where we've been posting lots of our Guide to Space videos and really cool interviews with astronomers. Patreon.com/Universe Today if you want to see how you can get involved in the Universe Today community. So the next thing is going to be the Virtual Star Party on Sunday night, and I'll be in transit, but I hope to make it back in time for that. And then on Monday, Sandy is going to join me and Pamela for a very special episode of Astronomy Cast, which was what happened at the Lunar and Planetary Science Conference, which Pamela had to miss, but Sandy got to go, and she will tell us what she saw and what she learned. And so we're looking forward to that. Sandy, of course, has been in the Weekly Space Hangout quite a bit, and it's always a treat to talk to her. So thank you, Nicole, for bringing her into our orbit, which is just great.
That was Pamela, actually.
Was it Pamela?
Pamela introduced me to her, and then So, yeah, you can totally thank Pamela for introducing us to Sandy. She's awesome.
Yeah, we've got her deeply ingrained into the process now, which is great. All right, well, hey, thank you everybody for watching. Thanks to the panel for joining us, and thanks for going deep on this discovery, confirmation of inflation. I've been looking at the Q&A, and a lot of people have said this is one of the best explanations that they've seen, even better than Professor Ryan Cox using a piece of paper on the BBC to try and so.
Nice.
It only took two of us 20 minutes.
So 20 minutes of me just asking questions like a 4-year-old until we got to the bottom of it. So
I still don't understand it.
Yeah, I think that was great. So thanks everyone for watching, and we'll see you all next week.
And so I had to let the computer run the Hangout without me while I went next door to George's office.
It was a learning experience.
It was a learning experience for learning space.
For learning space. Let's learn how to use our computers. Let's learn that we can't trust computers, that we're one step away from the total robot apocalypse.
I'll be the first against the wall.
Yeah. I, for one, welcome our screeching computer overlords. All right, so this week we've literally got one topic.
No, we don't.
One
No, we
big
don't.
topic that's
No, we
going to
don't.
just consume us all, and
One
every time
important
There's
topic.
because
Brian-
somebody canceled last
And
week
it's
when
Cosmo
another
Club.
organization had a big press
Brian
release.
and Matthew get tired, I will rile them up and send them back into battle against each other. It's just going to be a knockdown, drag out fight. So I'm really looking forward to this. But in addition, perhaps, maybe, we might also talk about some other things, such as how people can map the moon, just like the pros.
You're such a good partner, Fraser.
We'll be
Such a
talking.
good partner organization.
We'll be talking about waves on Titan. And I would love for us to talk a bit about Cosmos, because that's apparently what everyone does all the time, is talk about Cosmos. Some people even do live shows right after each episode where they talk about it, which is our good friends over at Astronomy Magazine have been doing that, and Discover have been doing a wrap-up. And also there's a bunch of exciting stuff happening in the sky shortly, and normally that's Dave Dickinson, but Mike Simmons knows as much about all that stuff as anybody, so he'll be catching us up on that. So without further ado, let's talk about the There we go. Hey everybody, welcome to the Weekly Space Hangout. My name is Fraser Cain. I'm the publisher of Universe Today, and we have all of our friends this week gathered together to talk about mostly about inflation and confirmation of inflation in primordial gravitational waves. So, and I am so glad we've got an all-star cast. Now, yes, I'm in a new location. Get over it. Moving on. So we've got Brian Coberline. Hey, Brian.
Hi.
From RIT. Dr. Matthew Francis. Oh, I could not be happier. We've got Dr. Matthew Francis versus Brian Coberline. Oh, this is the best. Mike Simmons from Astronomers Without Borders. Hey, Mike.
Hi, Fraser.
We've got Morgan Renberg. Hey, Morgan.
Hi, Fraser.
And Dr. Nicole Gallucci.
My audio works now. Yay!
Yay! That was
Yay.
close. It almost didn't work. What did you do? You turned it off, turned it back on again?
Yeah, I reset the PRAM. Mike can tell you, on Wednesday night, my speakers just decided to flip out and make this really high-pitched, well, you didn't hear the noise. They made this really high-pitched noise just as I hit broadcast.